We often imagine atoms as permanent building blocks of matter, tiny, unchanging, and perfectly stable. But reality is very different. At the nuclear level, stability is not guaranteed. Some atoms are constantly trying to rearrange themselves to reach a more stable configuration. And when they do that, they release energy. This process is what we call radioactivity. So here is the real question. Why do atoms decay on their own? No external force, no trigger, no collision, just spontaneous transformation. This is one of the most fascinating aspects of nuclear physics. A nucleus can sit quietly and then suddenly emit radiation without any warning. To understand this, we need to go deeper into the idea of nuclear stability. At the heart of every atom is the nucleus, made of protons and neutrons. Now, stability depends on a delicate balance. Protons repel each other due to electric force. Neutrons help stabilize the nucleus. So what determines stability? The key factor is the neutron-to-proton ratio, N/C. If this ratio is balanced, right-pointing arrow nucleus is stable. If it is too high or too low, right-pointing arrow nucleus becomes unstable. You can think of it like a system trying to maintain equilibrium. Too much imbalance, and the system will try to correct itself. That correction process is radioactive decay. To understand this balance, we must look at the forces inside the nucleus. There are two main competing forces. 1. Strong nuclear force, extremely powerful, acts at very short range, binds protons and neutrons together. 2. Coulomb repulsion, acts between positively charged protons, pushes them apart. Long-range force, so inside the nucleus, strong force tries to hold everything together. Coulomb force tries to push protons apart. If the strong force dominates right-pointing arrow stable nucleus, if repulsion becomes too strong, right-pointing arrow instability. And that is when decay begins. Now let's connect this to instability. The primary reason for instability is right finger imbalance in neutron-to-proton ratio, N/C. There are two cases. N/C too high, right-pointing arrow too many neutrons. N/C too low, right-pointing arrow too many protons. In both cases, the nucleus is not in equilibrium. So what does it do? It transforms itself by emitting particles or radiation to reach a more stable state. This transformation is what we define as radioactivity. Now we can formally define it. Radioactivity is the spontaneous emission of radiation from unstable nuclei. This radiation can be particles or electromagnetic waves. During this process, an unstable nucleus right-pointing arrow transforms right-pointing arrow into a more stable nucleus and releases energy in the form of alpha particles, beta particles, gamma rays. This is not a chemical change, this is a nuclear transformation. There are three primary types of radioactive decay. 1. Alpha decay. Emits an alpha particle, 2 protons plus 2 neutrons, heavy nuclei become lighter. 2. Beta decay. Neutron converts into proton, or vice versa, emits beta particle and neutrino. 3. Gamma decay. No change in composition, only energy released as gamma radiation. So depending on the type of instability, the nucleus chooses a different decay path. Now comes the most interesting part. Radioactive decay is completely random. You cannot predict when a nucleus will decay, which nucleus will decay next. Even if you observe a single atom, there is no way to determine its exact decay time. Each decay event is independent, and importantly, external factors like temperature, pressure, or chemical state do not affect radioactive decay. Graphically, radioactive decay follows an exponential curve. Starts at maximum value, decreases continuously over time, never actually reaches zero. At each half-life interval, value reduces to half. This curve is smooth and predictable, even though individual decay events are random. This is a beautiful example of right finger random behavior, right-pointing arrow leading to predictable patterns. But here is the surprising part. While individual decay is random, large numbers of nuclei follow a very predictable pattern. This is where statistics comes in. If you take a large sample of radioactive material, you cannot predict individual decay, but you can predict overall behavior. This leads to a very important concept, right finger half-life. Half-life is defined as the time required for half of the radioactive nuclei to decay. Let's visualize this. Start with 100% nuclei. After one half-life, right pointing arrow 50% remain. After second, right pointing arrow 25%. After third, right pointing arrow 12.5%. And so on. Notice something important. Half-life is constant for a given isotope. It does not depend on amount of material, external conditions. This makes it a very powerful and reliable concept. Now let's formalize this mathematically. The number of nuclei at time t is given by n t equals n0 e caret minus lambda t, where n t right pointing arrow number of nuclei at time t, n0 right pointing arrow initial number, lambda right pointing arrow decay constant. From this, we get right finger half-life formula, T1, 2 equals lane, 2, lambda. This equation tells us larger lambda right pointing arrow, faster decay right pointing arrow, smaller half-life. Smaller lambda right pointing arrow, slower decay right pointing arrow, longer half-life. So half-life is directly linked to decay probability. Now let's connect all of this to real life. Radioactivity is not just theory. It has powerful applications: medicine, cancer treatment, radiotherapy, diagnostic imaging, energy, nuclear power generation, archaeology, carbon dating for age determination, industry, material testing, thickness measurement. So what started as nuclear instability becomes a tool for modern technology.